Okay, hi students. As per request, some of you guys are still like confused with the theory part, right? So I will do a video recording in English, fully English, to talk about the theories lah. Now we start with the chapter 5, which is concurrent process. In chapter 5, we focus on parallel processing. Okay, what is parallel processing? Which means your computer system, you have more than one CPU. So if you look over here, the definition, the process of operating two or more CPU, which means more than one CPUs, okay, in parallel. The meaning of in parallel means at the same time. So parallel processing means at the same time I have more than one CPU that are running together. So here, process of operating two or more CPU in parallel with more than one CPU executing instructions simultaneously. Okay, each CPU can have a process in a running state, and we need processor manager to have to coordinate activity between each processor and to synchronize. So today, if you only got one CPU, then you have numbers of process. You should let the process to queue. You run one after another. But today, the system have more than one CPU. Let's say you have three CPU running in at the same time. Now you have numbers of process coming in, right? So you need to coordinate, you need to synchronize. So like you have three CPU, you need to say CPU 1 is going to run which process, CPU 2 is going to run another process, and CPU 3 is going to run maybe process D to make sure that they don't clash with one another. That's why synchronization is required in this case. Now, there's two reasons. First of all, synchronization is used to resolve the conflicts between processor. And second of all, what we want to ensure that all the events occur in proper order. Okay, so this is the major thing. Now, those development, you can read it on your own. As I say, I won't go into it, similar to what I say during the physical class, yeah? Okay, what we'll focus on will be synchronization mechanism, okay? Now, we know that synchronize is important, so that they don't clash among one another. But how do we ensure this synchronization? How do we do the synchronization, right? We need a mechanism to do that, okay? And to explain to you, because it's online, right? So to explain to you in a more easier way, we look into this diagram. Okay, how many process do we have? We have process A and we have process B, right? Okay, so how do we ensure synchronization? We remember two keywords. One is you need to know what is critical region, and two, you need to know what is mutual exclusion. So in this case, I will explain both of the terms here. Now, process A and B, they are running. So you see the straight line here, they are running. Now at T1, time 1, the process A enters into critical region. So here comes the first keyword, which is critical region. What is critical region? It is part of the program. Let's say I'm running a game or I'm running a system, right? Okay, when I'm running that process, it goes through the critical region. It means that it is running a part of the program that is very, very important in a way that you don't allow people to access to it. So a critical region is part of the program that must complete execution before any other process can access to it, because it is so important, so crucial. Until when I'm in critical region, I cannot allow any interrupt. I cannot allow other process to access to me. Okay, so that is what we call critical region. So what happened is like at this T1, A enters into critical region. Okay, what about T2? T1, T2. At T2, the B attempts to enter to critical region. Attempts doesn't mean that process B is in critical region right now. Process B is just attempting. And what we see here is after B attempt, B got blocked. Why? This is because mutual exclusion. Okay, here comes the second keyword, mutual exclusion. Mutual exclusion means that when one process is in critical region, no other process can be able to enter into critical region. That's why at T2, our process B attempt to enter into critical region, it got blocked because of mutual exclusion. So what is mutual exclusion? One process cannot access the critical region while another process is inside. That's why B is blocked until T3, where the A leave critical region and now B can enter into critical region, and once it leaves critical region, and the other process can go into. So here comes the two keyword, the two terms, critical region and mutual exclusion. Okay, next one, we go to semaphore. Okay, now we learn binary semaphore. We have 0 and 1 to indicate. Okay, you have to remember semaphore. You have wait and signal. I repeat, in semaphore, you have two operations, which are wait and signal. Okay, so to explain to you what semaphore is, right, you have to listen closely. Now, by default, the semaphore value is having a 1. Okay, all the semaphore value, look at this diagram, is having 1. Before a process can go into critical region, you need to call semaphore wait. Okay, before an operation go into critical region, you need to call the function semaphore wait first. Okay, the moment you call wait, it is going to do decrement. That's why you see S minus minus. So imagine I say default value you have 1. Now I call wait operation. I will do minus minus, then my semaphore value becomes 0. You see that? Okay. So when my semaphore value is 0, it means that the process is currently in critical region. We need to ensure mutual exclusion. No other process can go into critical region until it is done. Okay, when the process finishing the critical region, it will call signal. So when you call signal, you got a plus plus increment. So just now it's 0. After you call a plus plus, it will be 1. So it back to the default semaphore value. Okay, for whatever I'm talking here, if you think that it's quite confusing, I strongly recommend you to read out this one, because I'm just explaining this thing. Okay, I just put into not put into words like this is put into words like for whatever I'm highlight here. I'm just trying to elaborate with the basic term. Okay, so if you look into here, you will see that okay, semaphore value is 1 by default. You need to call wait system call before we enter critical region. Okay, and also the semaphore will test s smaller than equals to 0. Okay, so in this case, since default is 1, so not in the condition of here, which is no operation, so we will decrease the value of s and then go into the critical section. Okay, so if context switching is occur, no other process can go into the critical section because s is 0 until we done already, we signal. So when we signal, 0 become 1. Okay, so other value, not other value, other process, they can go into critical region. So that is what happened here. Okay, the next one, we have process cooperation. We talk about producer consumer cases and reader writer cases. Okay, look at the producer consumer. So what is producer and consumer? Listen closely. Producer produce data. Consumer consumes data. So producer, when they produce the data, will store in the buffer as a temporary storage, and consumer, it will consume from the buffer. Now it will happen in 3 different ways. The first one is the normal one. The producer produce into buffer, consumer consume, nothing happened. The second one is producer produce too fast. Your buffer is full already. Consumer tak sempat, like can't consume everything. The consumer is like, wow, the buffer is full, but the consumer still can't consume the data yet. Okay. Other way around, your producer is not producing any data. It's producing, like trying very hard to produce data, but it's not there in the buffer. So your consumer keep on consuming on an empty buffer. Consumer read, why but empty? Read, empty again. Okay. So when you have producer and consumer to work together, that's why we call cooperation. We need to implement 3 semaphore. So how do you implement? The answer is here already. So we indicate where is the full position, we indicate where is the empty position, and we also ensure there's mutual exclusion happen between these processes. Okay. Of course, you need to know, if let's say today your buffer is overflowing, like too much data in your buffer, we can delay our producer lah. Okay. Producer producing too fast. Consumer can't consume them at all because like it's too fast already. The pace is too fast. So what happened is that we just ask the producer to slow down a bit. So other way around, if the buffer is empty, we ask consumer to slow down. Okay, this one by right should be okay. Just hold on. Let me continue. Okay, now we go to the next one, the next cases, which is reader and writer. Okay, what is reader? What is writer? To make it simple, you have a database. The readers is just to read the data out. The writers are going to modify the data in the database. Okay, so in this 5.3.2, we give an example where we are using airline reservation system. So such as AirAsia. Okay, if you have ever used AirAsia to check on flights information or book a flight, then this is the cases for reader and writers. How do we work together? Now we go to the first one, which is readers. Readers are there to just read the data. Do readers modify data? No. So no one is changing the database, right? So in this case, we don't need mutual exclusion if we just have readers. If the whole system, the whole platform is just for people to read, then you don't need to do mutual exclusion. But in airline reservation system, in AirAsia, we don't just let people to read the flight information, we let them to book as well, right? So we have people who book the flight or make changes to the data, we call that as writers. Now, writers are those that are going to make reservations on the flight. So in this case, if you imagine you have reader and writer happen together, you need mutual exclusion or not? Yes. Okay. If you don't apply mutual exclusion, what will happen? It's like person A book for the flight, book for the seat 25. The person B also book for the same seat, you also allow. So that comes to error, right? So mutual exclusion is very important. If you don't implement it right, what will happen is like the same seat, it might occur two or more person booking for the same seats. Okay, so in that case, in order to handle this cooperation, we have the procedures to call by readers and writer. So like if readers want to do, first of all, they have to check whether the resources is readable or not, and is it available, okay? And also they check if there are any writers waiting. Now, if the writers are going to do something, so the writers have to check if the resource is able to write as well. After checking or able to write, now they also need to check is there any readers are waiting lah. Okay, to solve the cooperation, those mutual exclusion, right? You can use P and V. Now, this one is much more easier compared to the semaphore that you have known. It's just you giving priority to either side. So if you give priority to readers, when there are readers, you ask them to read first, the writer have to wait. If you give priority to writers, you ask the writer to write first, and if there's any incoming readers, you ask them to wait. So that's what happened. Okay, last part, concurrent programming application, which is this call begin and call end. Okay, this one, I worry a lot of you don't understand the structure or the information or the idea of call begin and call end. So you listen carefully for call begin and call end. If today I write call begin, okay, I write something here and I end with call end, right? Okay, first of all, you look at this question, it doesn't mean from top until bottom, from first equation until last equation, you need to embed with this call begin and call end. Okay, you only use it when you need to. So now let me explain call begin and call end. When you write something in between call begin and call end, for example, me myself, I write Winnie is sleeping, Winnie is eating, Winnie is singing, and I wrap with call begin and call end. That means Winnie is sleeping at the same time, can eat at the same time, and can sing. So I'm basically eating, sleeping, and singing, doing these three things at the same time. Do you think this is logic or doable? No, right? It doesn't make sense, right? So I can't put inside call begin and call end. Okay, see the difference? When you write the equations, you wrap with call begin and call end, which means you at the same time you are doing all the equation running all together at the same time. So if you get the idea of at the same time, then you know, okay, what are the equation that I can do at the same time? Not wrapping everything in the question into call begin and call end. Okay, last part about this theory, explicit and implicit parallelism. Now, if we're talking about implicit, it's like when you use your calculator. You press A plus B times C plus D. Okay, what your calculator will do? It will do the B times C first, right? So that is what happened. The compiler already automatically know what to do. This one we call implicit. Okay, but if we as human, we as programmer, we tell them what to do, what to execute in parallel to calculate which one first. Let's say I say, okay, you have to calculate A plus B first, then only followed by C plus D. Okay, and then only you times, okay, you multiple the first A plus B with C plus D. Now, when you are trying to tell system the instructions to execute in parallel, that's what we call explicit parallelism. Okay, so that ends with chapter 5 theory. If you still got any question, you can email to me. Try to reach me with this Google chat things. Okay, so I shall see you during the revision.